The last thing we need to cover for this chapter is reaction mechanisms. So this goes to the idea that reactions can, and many times do, proceed in multiple steps. So we'll go ahead and write this out. These steps involved in a reaction. Reactions can be multi-step, producing intermediates. So that's kind of a new term. Intermediates that are consumed in a later reaction step. So we could have multiple steps in here. So let's give a little bit of an example. We'll do hydrogen peroxide. And if we add in some iodide ions, like sodium iodide, what we'll see happen initially, actually we won't see this happen, but what does happen is you get a couple of products. But one of the products, iodate, will further react with the hydrogen peroxide and break that down, kicking the iodide back out, producing more water and some oxygen. So this is like a step one versus step two. They both occur. Step one happens first, followed by step two. Now, just to identify a couple things here, this product is what's called an intermediate. An intermediate is something that is not present in the beginning of the reaction. The beginning of the reaction is the only thing here. So this is produced in the reaction, an intermediate. Here it is. And it is consumed in the second step. And it does not show up at the end of the reaction. So as far as the reaction goes, you never see it. You see what you had in the beginning of the reaction, and you see what you have at the end of the reaction. This, found on both sides of the arrow, yield sign, is produced and consumed. It's gone. Now what's interesting is having iodide present in the beginning of the reaction, and then you see it at the end of the reaction, as if it wasn't involved at all, but clearly it was critical in forming the intermediate. Something that is present at the beginning of the reaction and is present at the end of the reaction is called a catalyst. But because it's found on both sides of the line, we cross it off. Everything else that we have here, we're going to drag down, keeping track of what's on both sides of the arrow. So for example, I have two hydrogen peroxides, and they decompose, actually reacted, but I'll just say that, to form some water and some oxygen. Now this would happen all on its own. If I didn't have this reaction here, I could say, yeah, this will happen, it'll decompose. It happens slowly. But when you introduce a catalyst, the reaction goes much more quickly. And again, you have an intermediate formed and it is consumed later on. Okay. We had a few more notes here and we'll just keep plugging along. In a multi-step reaction, very important, the slowest step is rate determining. Oops, no period. And provides the rate law. So that tells us what the rate law is going to be, that slowest step. And given here, I didn't actually get into that here. This is just kind of an introduction. But let's go and do another problem, one more problem, and we'll see how that would shape up in that little example. Okay, I have an equation that would be 2NO plus Br2 produces 2NO Br. And just looking at it, I'd like to say, okay, this is the reaction. But remember, a long time ago in lectures, we stated that you cannot simply look at a reaction and say, okay, this is going to be second order with NO and it's going to be first order with Br2. You have to determine this experimentally. Now, it may turn out that these exponential values or these coefficients are the exponents, but we don't know that. We can't just state it because there could be multiple steps. But if I know there's multiple steps now, and they're all elementary, we can then therefore say the slowest one determines how fast it goes. So let's take a look and see if we do have some steps here. Well, we do. I'll just tell you what they are. We have a step 1, and it is NO plus Br2. And I'm just going to go ahead and put this in, and I'll talk more about it in just a moment. And it produces this. I will tell you ahead of time, this reaction is fast. For the fact there's a step 1 implies that there's probably a step 2. That NOBr2 reacts further, some of it anyways, with some NO and runs to completion, producing some NOBr. And this is a slow step. Now this creates a bit of a problem. So imagine like having this go. So it's ready, set, go. This just blasts over the products. And then as it sits there, some of it kind of dribbles into the second step and slowly makes its way through producing products. So it kind of gets bogged down. Now what we were saying in the notes just a minute ago is the slow step is rate determining. So we'd like to say, oh, well, therefore this is going to be the reaction or create the rate law. Problem. If I'm sitting here in the lab and I haven't run the experiment yet, I have these two reactants. I don't have any NOBr2. This is an intermediate. Intermediates cannot show up in the rate law because you don't have them. They're just something that are produced and they're easily consumed in the second step. So therefore, I have a bit of an issue. So what we have to do is go and make a substitution for this, which are these two guys here, the reactants, because it goes back and forth. So again, what happens, this is produced, it gets stuck here because it just kind of dribbles. So what happens is this goes back and forth and it creates what's called an equilibrium. So it just kind of goes back and forth here producing it. It goes very fast here and kind of dribbles back and forth, and you get this back and forth reaction here. So these two guys can be substituted for each other. Instead of writing this, I can write these two guys. So let's see how this would play out. I can rewrite a rate law, and I want to do it off the slow step, right? So I have this K, but in place of NOBr, which I can't use, I'm going to substitute these guys in for it individually. NO, Br2, and then I'll just continue on with everything else, which happens to be one more product, or excuse me, reactant. Now having this, notice these guys are the same, and if I multiply by itself, it just so happens to be, just by coincidence, to the second power, which is what I had up here. But again, it's just by coincidence. And this would end up being the rate law for that equation. So just to mention again, whenever a slow step comes after an intermediate is formed, and we can substitute into the slow step. Now, just to be clear, if the slow step was first, right here, if this was slow, fantastic. Boom, boom. That would be my rate law, would be based off these two guys right here. That works fine. If slow step is first, rate law based on those. But if slow step is second, you have to do what we did in this little example. All right. Almost done. Just to mention, this will take about 1 minute. A catalyst. This is something a little bit different than what you might just want to say. The easy answer is say, well, what does a catalyst do? It lowers the activation energy. No, it doesn't. What a catalyst does, it provides an alternative. An alternative pathway that has a lower activation energy. So the reaction goes more quickly because of the lower activation energy, because of the different pathway. Okay, that is the end of the lecture for chapter 14.